Hey there, it's Shannon Magic Myers, and today we'll be checking out tangent planes and normal lines. So first of all, let's warm it on up by finding the general equation of the plane containing the points P, which is at 2, 1, 1, Q, which is at 0, 4, 1, and R, which is at negative 2, 1, 4. So pause the movie, warm it on up, and let's do this thing. Okay, so see how you did. Why don't we let the vector u equal to PQ, the directed segment PQ, which would be equal to the vector 0 minus 2, 4 minus 1 in the component form, and then 1 minus 1, which is negative 2, 3, 0. And we can let V equal to, let's see, how about QR, the directed segment QR, which would be negative 2 minus 0, 1 minus 4, and then 4 minus 1, which would be negative 2, negative 3, 3. Cool so far? Okay, so U cross V is equal to, let's see, we have I, J, and K, and then negative 2, 3, 0, and negative 2, negative 3, and 3. And that will equal to I times, let's see, 9 minus 0 minus J times, I'm just doing the determinant here, negative 6 minus 0 plus K times 6 minus negative 6, so 6 plus 6. Cool, cool? All right, so that will be 9I plus 6J and then plus 12K. So that would end up being what? In component form, 9, 6, 12, which if we factor out a 3, would just give us 3, 2, and 4. And so that gives us that n, right, our normal vector to the plane can be equal to 3, 2, 4. And so that gives us that A is 3 for our direction numbers, B is 2, and C is 4. So continuing with that, we will have, three times x minus, I'll go ahead and choose, you can pick any of the points to use. So we'll just pick point Q. It's got a 0 in there. So 3 times x minus 0. And then, what else did we have? Sorry. Plus 2 times y minus 4. And then plus 4 times z minus 1 would equal to 0. So that would be standard form, right? And what will that give us? That'll give us 3x plus 2y minus 8 plus 4z minus 4 is 0. And simplifying, we would get 3x plus 2y plus 4z would equal to 12. And we're done. Cool, cool? All right, so next up, let's look at the definition of tangent plane and normal line. So let f, capital F, be differentiable at the point P, which is x0, y0, z0, on the surface given by capital F at x, y, z equal to 0, such that del f at x0, y0, z0 is not equal to the 0 vector. We're going to assume that for the rest of this section. The plane through P that is normal to the gradient of f at x0, y0, z0 is called the tangent plane. To S, so to the surface S at the point P. The line through P having the direction of the gradient of f at x0, y0, z0 is called the normal line to the surface at the point P. Note, we've been using z equal to function of x and y, right, for some surface S. If we rewrite this as 0 is equal to f at x and y minus z, right, what you have is the surface S, which is the level surface of some f, capital F, given by capital F at x, y, and z equal to 0. Okay? So you're just, since f at x and y minus z equals 0, what we have is a level surface, and so therefore if we write it in terms of the three variables, capital F at x, y, and z, that will also equal to 0. Okay? So, first example, let's find a unit normal vector to the surface at the given point. So, here's a hint. We want to normalize the gradient vector. LF is at x, y, and z. So, we've been given the surface x squared plus y squared plus z squared is 11, and we're interested at the point P, which is at 3, 1, 1. Cool, cool? Okay, so the gradient of f in general at x, y, and z, remember, is going to be the first partial of f with respect to x at x, y, and z times I, because the gradient is a vector, plus the first partial of f at y, or with respect to y, plus, or times j, plus the first partial of f with respect to z times k. Cool so far? Awesome. So, gradient of f in general will be equal to, so treating everything as a constant except for x, what will we have? Beautiful. We will have 2x times I, and then we'll have 2 plus 2y times j, and then plus 2z times k when we do the partial derivatives. And now we're interested at del f at 3, 1, 1. So we'd have 2 times 3 times I plus 2 times 1 times j plus 2 times 1 times k. And of course I just got that. Wherever there was an x, I put a 3. Wherever there was a y, I put a 1. And wherever there was a z, I put a 1. Groovy? All right. So del f will be, at 3, 1, 1 rather, will be 6i plus 2j plus 2k. Cool, cool? All right, well, we want to normalize this, right, because we want the unit normal vector. So we basically just want to find del f at 3, 1, 1 divided by the magnitude of del f at 3, 1, 1. And that will be we can factor out a 2 and then times the vector 3, 1, 1 over the square root of, we'll just have a 2 times the square root of 9 plus 1 plus 1, which will be, these 2's will divide out, and we'll get a 3, 1, 1 times 1 over root 11. Groovy? And we're done. All right, so moving on, we've got a theorem, equation of a tangent plane. If f is differentiable at x0, y0, z0, then an equation of the tangent plane to the surface, which is given by capital F at x, y, and z equal to 0 at x0, y0, z0 is going to be fx at x0, y0, z0 times x minus x0 plus fy at x0, y0, z0 times, that's my cat, y minus y0 plus fz at x0, y0, z0 times z minus z0, and sorry, let me move this over. And that is all equal to 0. Cool, cool? All right, so basically all you're doing is you're finding, the directional derivatives at x0, y0, z0, and then multiplying that value to x minus x0. So here we go. Example 2, find an equation of the tangent plane to the surface at the given point. So h at x and y is equal to natural log at the square root of x squared plus y squared at the point 3, 4, natural log at 5. So here we go. What we're going to want to do is rewrite this as z equals 1/2, I'm just using properties of logs, times natural log of the quantity x squared plus y squared. But in turn, we can write this as 0 is equal to 1/2 natural log at x squared plus y squared minus z. And so if we make capital H of x, y, and z, that will equal to 1/2 times natural log at x squared plus y squared minus z. So let's find those partials, okay? So we'll just do the work over here. So hx in general at x, y, and z is going to equal to, I'm treating y and z as constants. So I believe we'll have 2x over 2 times x squared plus y squared, which would just be equal to x over x squared plus y squared. And so that means that hx at 3, 4 natural log at 5 is just going to be 3 over 3 squared plus 4 squared, which will be 3/25. All right, so hy at x, y, and z will be very similar, but we'll end up with 2y over 2 times x squared plus y squared, which would be y over x squared plus y squared. And so hy at 3, 4 times 3, 4 and natural log at 5 will be 4 over 3 squared plus 4 squared, so we'll get 4/25. And then hz at x, y, and z will just be -1. So that means that hz at 3, 4, and natural log at 5 will just be equal to -1 as well. Cool, cool? Okay, so now we've got most of our pieces that we need. In general, remember the equation of the tangent plane to the surface at the given point is going to be hx at that point. So what was our point? 3, 4 natural log at 5 times x minus 3, because that was our x0, and then plus hy at 3, 4 and natural log at 5 times y minus 4, because 4 is y0, and then plus hz at 3, 4 natural log at 5 times z minus natural log at 5, because that's our z0, and that would all equal to 0. And so simplifying from the work we did over here, we'll have 3/25 times x minus 3 plus 4/25 times y minus 4, and then minus the quantity z minus natural log at 5, and that's all equal to 0. Cool, cool? Okay, so this format would give us the standard form, and if you want, you could put that in the general form by getting the x, y, and z terms on one side, but we don't need to do that. Cool? Okay, so next up, find an equation of the tangent plane and find symmetric equations of the normal line to the surface at the given point. So the surface is z equals arctangent at y over x, and the point is 1 pi over 4. Okay? So we're basically doing the same thing that we did before, same process, but this time we want to find the symmetric equations. So let's go ahead and do our work. So remember, f at x, y, and z is going to equal to arctangent at y over x and then minus z. So we need to find the partial derivatives, right? So the first partial with respect to x of x, y, and z is going to equal to, so we have the arctangent, right? So what's that derivative going to be? Beautiful. Remember, in the denominator, you're going to have 1 plus what's inside that arctangent squared, and then you're going to have the derivative with respect to x in the numerator, so that would end up being negative y over x squared, and fx at 1 pi over 4 will be, let's see, negative 1 over 1 squared over 1 plus 1 over 1, the quantity squared, which will be negative 1/2. Okay, so the first partial of f with respect to y be just slightly different. This time we will have in the numerator, we will just have 1 over x, and our denominator will be the same. And so then plugging in the values 1 pi over 4, we will have 1 over 1 over 1 plus 1 over 1 squared, which is again going to be 1/2. And then the first partial with respect to z is just going to be negative 1, which will equal to the first partial with respect to z at that particular point as well. Groovy? Okay, so we've got our partials here. So now let's go ahead and find the equation of our plane. So we will have, let's see, negative 1/2, because that's our fx at 1 pi over 4, and then that's going to be times x minus 1 plus positive 1/2 times y minus 1, and then minus z minus pi over 4 equals 0. And then, let's see, If I go ahead and multiply both sides by 4, I will have negative 2 times x minus 1 plus 2 times y minus 1 minus 4 times z minus pi over 4 is still equal to 0. So that'll give us negative 2x plus 2 plus 2y minus 2 minus 4z plus pi is equal to 0. And so I will end up with negative 2x, the 2's will 0 out, so plus 2y minus 4z is equal to negative pi. Cool so far? All right, so that's the first part. We found the equation of the plane of the tangent plane at the point. So that was all this. And now we need to find the symmetric equations. So to find the symmetric equations, what do we need to do? Remember that you've got x minus x0 over a is equal to y minus y0 over b, which is equal to z minus z0 over c. Well, if you recall, our a, b, and c, now that we've got it in this format, are the coefficients to the x, y, and z. So we will have x minus 1 over negative 2 is equal to y minus 1 over 2, which is equal to z minus pi over 4 over negative 4. We're done. And so basically our A was the negative 2 here. Our B is the positive 2 right there. And then our C is this negative 4 right here. Groovy? Okay. So, here we are. Next up, we have example 4. Find the path of a heat-seeking particle placed at the point in space 225 with a temperature field T for temperature at x, y, and z equals 100 minus 3x minus y minus z squared. All right, so for this guy, what we're going to want to do is find the gradient, because we want to find the direction of maximum increase. Okay, so del t at x, y, and z, if you recall, is going to equal to tx at x, y, and z times I plus ty at x, y, and z times j plus tz at x, y, and z times k. Cool so far? All right. So that's going to give us del t at x, y, and z will be equal to negative 3 I minus 1 times j minus 2z times k. Cool so far? So basically what I found here is that, you know, so what we have here is we have that the instantaneous rate of change of x with respect to t is -3. Instantaneous rate of change of y with respect to t is -1. And the instantaneous rate of change of z with respect to t is -2z. So that would give us that dx is equal to -3 dt. In integrating, we would get x is equal to -3t plus some constant, call it constant 1. X at 0 would equal to c1, and c1 in turn is equal to 2. So we would end up getting x is equal to -3t plus 2. Similarly, we'd have dy is equal to -dt, and then y would be t plus, call it constant 2. Well, y at 0 would be equal to c2, which would equal to 2. So we're getting these are like our c1, c2, and c3. So it follows that y would equal to t plus 2. And I'm sorry, we'd have a negative right here. So dz would equal to 2z dt and then we would want dz over z would be equal to, and this is again is -2 dt. So natural log absolute z, when we integrate, would equal to -2t plus, we're going to work with this one a little, so we're just going to call this one constant c for the moment. And so now what we'll have is, remember, a logarithm is an exponent, so we're going to end up with e raised to the -2t plus c is equal to z, and that gives us e to the -2t times e to the c is equal to z. So what we'll have is we'll have e to the c, we can just call our constant c3, so we'll get z is c3 e to the -2t, and z at 0 is going to be c3 e to the -2 times 0. So z at 0 is just c3, which is 5. So z is equal to 5 e to the -2t. So now what we'll have here is we will have, remember what we're supposed to find is the path here. And so the path is represented by these three equations here that we found. So this one, and this one. Cool, cool? All right. Okay, so the angle inclination of a plane. So here you've got sort of a visual going on, or to get a visual going on, this is kind of what we'll have. So we'd have X, Y, and Z. Okay. And so what'll happen is you'd have some, some plane. We can have it look like this. We'll drop it this color. So we'd have something like this, and then you'd have some kind of angle of inclination. So it would be inclining up some amount theta, okay? And then you'd have your inclining plane, which will look something like this. And probably more like this. So this is like the inclining plane. And then, so then what happens is you've got your normal vector to the plane, and that of course is at a right angle here to this plane. And then you've got this K, and K is the unit vector that's normal to the XY plane. So basically, sorry. So basically, you'd have something like this. This would be the K, and then theta, this would be theta as well. Cool. So that's what's going on. So basically, long story short, the angle inclination of a plane is given by cosine theta equals the absolute value of the dot product of n and k divided by the magnitude of n. All right? So here we go. Last theorem here. The gradient is normal to level surfaces. So if f is differentiable at x0, y0, z0, and del f at x0, y0, z0 is not the zero vector, then del f at x0, y0, z0 is normal to the level surface, level surface through x0, y0, and z0. So let's go ahead and look at an example that would pertain to that. We'll go ahead and add a page here. So if we call this example 5, let's find the angle of inclination of the tangent plane to the ellipsoid x squared over 12 plus y squared over 12 plus z squared over 3 equal to 1 at the point call it P 2, 2, 1. All right, so what we would want to do is we can name capital F at x, y, z equal to, beautiful, x squared over 12 plus y squared over 12 plus z squared over 3 minus 1. And then what's our del F going to be? Good. Del F at x, y, and z will just be 2x over 12 is x over 6, so times I, plus y over 6 times j, and then plus 2z over 3 times k, and gradient of f at x, y, and z will be plugging in 2, 2, 1. We'll have 2 over 6 times I plus 2 over 6 times j plus 2 times 1 over 3 times k. And sorry, that was at the particular point 2, 2, 1. So we will have del f at 2, 2, 1 is 1/3 I plus 1/3 j plus 2/3 k. Cool so far? All right, so then del f at 2, 2, 1 is normal to the tangent plane and k is normal to the xy plane. So cosine theta is going to equal to the absolute value of del f at 2, 2, 1 dot k over the magnitude of del f at 2, 2, 1. So we'll have cosine theta is we have 1/3, 1/3, 2/3, dot 0, 0, 1. That's the absolute value over the square root of 1/9 plus 1/9 plus 4/9. So cosine theta will be equal to 2/3 over root 6 over 3. And then cosine theta will be equal to 2 over root 6. And we would have the angle of inclination would be, let's figure that out. Let me see what mode we're in. Let's do this in degrees. So we'll have arc cosine of 2 over square root 6 so we get approximately 35.3 degrees for theta. Cool. All right. So that's it for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe and tell your friends. All right. Bye.